Okay, yeah. Okay, so in the last class, we were looking at the hydrogen atom problem using the Dirac equation, and we had written down uh, two equations which are right there on the screen right now. These are both first order uh, but coupled differential equations. Uh, the derivative of f is related to g and derivative of g is related back to f. So if you eliminate, then you would get a second order linear differential equation, and it should be solvable. What we did last time was that we did singularity analysis of these coupled equations, and we said that r equals 0. uh, that was the original set of variables. So rho is something we defined at r equals 0. So these are the original equations, and we said that r equals 0 and r equals infinity were singular points, and then we also saw that r equals 0 was a regular singular point, whereas r equals infinity was irregular singular point. Then we uh, looked at these equations. We said that, like, if you take r very large, then you can ignore the terms which fall off as 1 over r. uh, this term also in some sense falls off at 1 over r, but if you ignore that, then the equation is not even a differential equation, so you typically don't do that. You just look at coefficient functions which fall off fast as you go to a singular point. You drop those terms, then you get df by dr is equal to some constant times g, and dg by dr is some constant times f. So if you eliminate this, you can easily check whether the solution is an exponential function. Okay, so that's the solution that we had written down. We chose one particular sign because we want our wave functions to be, or solutions to be well behaved, or what in quantum mechanics we say we want our wave functions to be square integrable.
So
Hmm.
here, at r going to infinity, like far away, we know the form of the function.
Yes.
So, and in general, we need to solve for all r,
Yes.
which we'll do in the next steps.
Yes.
So, will we expect that solution to converge to exponential minus AR?
Yes. Yeah. Yeah.
Then, when we said that the series truncates,
Yes.
how will that ever converge to this?
Oh, because uh, the total solution is e to the minus ar times the solution that you obtain at r equals 0. Okay. In the neighborhood of r equals 0, e to the minus ar is not playing any role at all, because e to the minus ar near r equals 0 is just a constant.
But in general, it does, like at any r not equal 0, it plays a role.
Yes. Yeah. So therefore, the solution is e to the minus ar times whatever is the solution at r equals 0. Okay. Is that fine?
I am not so sure, but okay.
What one needs to do is to basically check this by writing down a solution which is whatever you solve at r equals 0 times this expression, and explicitly check that it works. Okay.
Yeah, I mean, yeah.
Okay. When we'll do the differential equation stuff, we'll kind of get a little better picture of what we are trying to do here. Okay. This is something, since it's in a very specific context, that would be a little more general. All the solutions that we are obtaining are local solutions, really. And their validity has to be kind of checked by looking at the behavior of the solution. Okay.
So I'm not sure whether it's related, but even when we solved for in electrodynamics or somewhere else and we got Legendre polynomials,
Yes.
there also we demand some sort of a truncation.
Yes.
But I don't really know whether the reason for that is this only.
Well,
Like,
well, in the legendary case, you demand the truncation simply because you want I mean, you want the solution to be well behaved at r. What is that? X equals plus or minus 1, right?
yeah,
So that would tell you that the solution that you would write down would be a polynomial form, Okay, and that polynomial form has to has to have a structure where it vanishes at x equals plus or minus 1, okay, by finite power. Okay, if it vanishes with infinite power, then that would mean that those points have essential singularity. But the differential equation doesn't have irregular singularity; they are regular singular points. So you don't expect the solution to have essential singularity there by Frobenius theorem. Okay, so that would tell you that you should be looking at a solution which is polynomial, which has finite order zero there. You take finite number of derivatives, after which the quantity just vanishes. Okay.
Okay.
Yeah. So okay. So coming back to this one, we said that the leading behavior of the solution is uh, at r equals infinity is something like exponential, and then let's try to look at the solution at r equals 0, and for that we change the variable r to rho, so that we can kind of soak up these factors of a that are lurking around. I have put alpha, which I had not written earlier, to be e squared upon 4 pi, which is the one which is being used here and was not used before that, if I'm correct. Okay, so fine. So this alpha is basically just a fine structure constant, and these are the two equations. And since rho equals 0 is a regular singular point, we will substitute the Frobenius series solution, which is of this form. Okay, and we did this stuff last time, and we got these equations. Okay, so this is a straightforward substitution. Uh, as I said last time also, it's easiest to write this as fn rho to the n plus s, and similarly gn rho to the n plus s, so that when you differentiate with respect to rho, you just get a n plus s out directly. Okay, it's kind of easy to keep track of that. It's easy to write it this way, but when you differentiate it, it's better to put the power inside itself. Okay, fine. So that is how you get n plus s factors. And here, k versus minus k are the relative signs sitting around here. That's how one of them is plus k, the other is minus k. And this minus fn minus 1 are these minus 1 factors sitting around here, and so on. So everything should be, it should be possible to trace from the previous equation. Okay. Okay, so once you do that, then we said that we will solve the initial equation, which corresponds to setting n equals 0, which is the leading term in the Frobenius answers, which would determine what is the value of s. And that, of course, assumes that f0 and g0 are non-zero, which was, of course, starting point for us. And once you choose that, and once you say that f0, g0 are not equal to 0 in this, then it just the determinant of the corresponding matrix vanishes. That is this equation. And that gives us the solution s to be these two values. We, of course, choose a positive sign. Okay. Uh, we are looking for a solution near r equals 0. If rho to the positive sign would tell you that the wave function is well behaved at r equals 0, negative power would have made it diverge. Okay, and in spite of having the exponential fall of the wave function at r equals 0, that is not useful. So therefore you really need to choose positive sign. Okay, now this is also something we talked about last time, that if you choose the lowest value allowed value of k, which is k squared is equal to 1, uh, which means k is equal to plus or minus 1, then it indicates that there is an instability when z times alpha is greater than 1, because in that case s is not even real. Okay, and uh, but this instability is fine compared to the kind of instability that we encountered in the Klein-Gordon equation, which would have said that uh, that z plus alpha by 2 should be greater than 1, or some such thing. That uh, it basically told us that uh, maybe the other way around. It basically told us that z should not be greater than 69. So I would think 2z alpha should be greater than 1. Okay, fine. The other thing that we can derive from this is that f0 upon g0 is given by s minus k upon z alpha. Okay, just use one of the equation to write down f0 upon g0. Okay, fine. Then we also did this manipulation, that we multiplied the first equation That is, I think, the reason why I had this thing pulled up. So I think we decided to multiply the first equation by e plus mc squared and second equation by square root of m squared c squared minus m squared c to the 4 minus e squared. And if you do that and subtract, then what happens is that the terms like these survive, and the terms and then there are other terms which would cancel. For example, the term involving fn minus 1 would cancel with this term, and a gn minus 1 term would cancel with this one. Okay, so whatever survives are just fn gn pieces, which is what is this expression. Okay, so what it tells us is that if you know fn's, you know gn using this relation. Okay, so that was the conclusion that we drew last time. Okay, now uh, this is what Kaustuv was talking about, that if we want to avoid this behavior, then we would say that the series terminates and then you basically have a polynomial solution. So there exists some n prime such that fn prime. Hello, can you hear me?
Yeah, sir.
Yeah, okay. My computer periodically threatens me saying that the internet connection is unstable. So I would periodically ask you this kind of questions. Okay, so if you demand this, then you can kind of put it back into this equation and determine fn prime in terms of gn prime. Okay, so this is basically just saying that, like, suppose n minus 1 was n prime, then n would have been n prime plus 1, but for n prime plus 1 these vanishes, both of them vanish, so therefore you can remove these and then you write down fn prime in terms of gn prime using this equation. Okay, which is what we did. This expression is precisely that. Okay, so now of course if you determine this relation, you can use the recursion relation to which is the relation between f's and g's, to determine uh, all of them in a systematic fashion. Okay, what we want to do is to also determine the energy eigenvalues using this relation. Okay, so to determine energy eigenvalues, what we will do is basically substitute the yeah, this is a very cluttered equation, uh, but what we'll do is basically that we use this fact that fn prime is equal to e minus mc squared upon square root of m squared c to the 4 minus e squared whole multiplied by gn prime, plug it into this relation. Okay, and simplify. Okay, so now notice that this relation is for arbitrary n prime. It doesn't have to be the highest n prime value. So you could choose it for arbitrary n prime, plug it into this equation and simplify. Okay, now of course you are assuming that when you replace fn prime by gn prime itself is not equal to 0, otherwise everything would trivially vanish. Okay, so if you do that, you get an equation which is something like this. Okay, so this is the equation that you obtain by actually multiplying these quantities. So it came from here. Okay, so once you kind of substitute fn primes in terms of gn primes and pull out the gn prime, you get an equation which is like this. For some weird reason, it is not keeping space between these two things, but anyway, you can check this. All I'm doing is substituting fn prime to be e minus mc squared upon that square root times gn prime, but gn prime is not equal to 0, so whatever is the remaining piece, this should have been minus sign. Disaster. Okay, it should be equal to 0. Okay, now all you need to do is to simplify this expression, uh, and the expression is not too complicated, although it looks a bit complicated. uh, but if you multiply e plus mc squared and e minus mc squared, you get actually e squared minus m squared c to the 4. So you can pull a sign out and remove the square root from the denominator and put it in the numerator. Okay, so that is the term which you get here. Okay,
So
yes,
would you go back in this upper half to the relation between fn prime and gn prime?
yes, yeah.
Also to the recursion relation in the lower slide.
Yeah, yeah, sure. Just hold on. Here.
Yeah. So for
Okay.
we are demanding that the series truncates at some n equal n prime.
Yeah.
So we are feeding that n equal n prime plus 1 and taking fn prime plus 1 as 0 and gn prime plus 1 as 0.
Yes.
And then we are finding out the relation between fn prime and gn prime,
Yes.
which is what you have shown in the upper slide.
Yes.
That is for n equal n prime highest, where the series truncates.
That is right. That is right. But what you find in this expression is that this relation, see, if it did depend on n prime, then it would have had a n or n prime dependence here. Like for example, here this recursion relation does depend on n, and you see the n appearing in the recursion relation. But once you get this expression doesn't have any explicit n dependence on this. So if you change the value of n prime, the relation continues to hold.
I don't see how that is so obvious, but
Also, is this consistent because for we set n prime such that n prime plus one part is zero.
Yes.
But if this is true for all n prime, then all n prime plus one part are zero. I mean, but that is
No. So it's like this, that you choose a solution of a particular kind. Like let's look at the harmonic oscillator problem in one dimension. Okay, when you say that the you are looking at, say, second Hermite polynomial, which is a linear function. Okay, then you say that the quadratic term vanishes. Okay, that gives you a linear solution. Okay, but when you look at, say, fifth Hermite polynomial, which is a quartic function, then you say fifth power of uh, I mean, fifth power appearing in the polynomial vanishes, right? So, n prime itself is a variable. You are not setting it, saying that, like, that, when you say n is equal to n prime such that fn prime plus 1 is equal to 0, that gives you one solution. Okay, we are doing an eigenvalue problem. There are infinite number of solutions to these equations. One solution per choice of n prime. Okay.
but let's say suppose I feed in the recursion relation some n equal n prime minus 1. No,
Yeah.
sorry. Yeah, n equal n prime I feed.
Yeah.
No, wait.
Yes.
Just a
Yes.
second.
No, you are right. N equals n prime.
Yeah, n
Then,
equal n prime I feed.
yeah.
So the I don't see how I'll go to 0.
Yeah. So what it will tell
I
you is that, like,
think,
how, excuse me.
yeah, what I was saying, you're trying to say that for every solution, the n prime will satisfy the same relation. It is not that
Yeah.
all the n's from 0 to n prime will satisfy the same relation.
No.
Only the highest factor
Only the
correspond.
highest fellow for any n prime.
Yeah,
Okay.
yeah, that is
Yeah,
fine.
yeah,
That's what. No. I'm not doing that, like n prime is equal to, say, 5, and I'm trying to solve for fn. I mean, let me go down, and I'm trying to solve for f, say, 3, and use this relation. No, I'm not doing that. If I choose n
yeah,
prime is equal to 5, then I'm giving the relation between f5 and g5.
Yeah,
Okay.
yeah, and that is fine. But for determining f4, f3, f2, f1, and f0,
I need a recursion relation that is
yeah,
independent.
and that we haven't done yet.
Oh, that we are not done. Not at
Yeah,
all. Yeah, certainly.
but like, are you also saying that without explicitly finding that we can do the energy thing,
Yes,
in what you have done
yes,
in the next slide?
yes.
Okay.
That is the point. That's precisely the point. You just need to look at the highest fellow, and it will give you the energy expression. Okay, that's what we are doing. Okay, if you look at the highest fellow would require you to look at this equation, which is the one which we are looking at just now. This equation. Okay, substitute this equation in that recursion relation. The next fellow is anyway 0, right? In this case, you substitute at this point, fn's and gn's are 0 because you are choosing these guys to be n prime. They are n prime plus 1. For a given choice of n prime, these fellows would vanish. This expression should be equal to 0, but you have already stated that Gn prime and Fn prime are not equal to 0. Okay, so therefore whatever is the expression should just vanish. Okay, so substitute Fn prime in terms of Gn prime, that is this factor, pull Gn prime out, and this equation should be equal to 0. Okay, that we need to simplify now. Okay, fine. So if you simplify that, you get an expression which is like this. Okay, I'm sorry for this mess. Give me a second, I'll get my equation straightened out first. Yeah. Just a second. Okay, it will correct it soon. Okay, uh, I cannot give the gap here, but at least it will give you a correct equation. So once you get that equation, all you need to do is massage it a bit. You take e plus mc squared, this thing, put this square root upstairs. By doing that, then collect the terms involving the square roots. You find that the terms involving square roots have k factors with opposite signs. So the k factor goes away and you get a term which is minus 2 times square root times s plus n prime. Okay. Factor of 2 comes because this term and this term gets added. Minus sign is here. This is e squared minus m squared c to the 4, but that is minus of the square of the square root. So that's why you pull another minus sign out. That gives you this term. And the other term that you have is a term that you can kind of easily check from this expression, which just sits around here. Okay.
1 second.
Yeah.
Could in the lower part, could you scroll down and
Yeah. So I hold on. Yeah, lower part I scroll down.
where we simplified the relation to get just Fn and Gn? Yeah,
Yeah,
this.
this one. Yeah.
In this, we are feeding that relation,
In,
right?
in, in this we
Fn.
are feeding it. Yes.
Yeah,
Yeah.
okay.
Exactly. Okay. So uh, sorry, this should be Z alpha. There's a typo there. I'll just correct it. Okay. But anyway, so what happens is that you get uh, so you get this expression simplified to this form. Okay. The first term that I just explained, that it is 2 times s plus n prime times this quantity. The second term is the square roots get cancelled. It is e minus mc squared, and e plus mc squared terms. The mc squared piece cancels. E adds twice z alpha. Okay, that is equal to 0. All you need to do is to take this one of the terms to the other side, square both sides. Then you get terms which are proportional to e squared on both sides. Collect e squared pieces. Okay, and write down this expression. Okay, so this is the answer. This is the spectrum. Okay. Now remember, this spectrum is written in terms of S, but S is the coefficient of the initial part of the uh, Frobenius solution, and that we have already solved. So S was square root of some k squared minus z alpha, or k minus z alpha or some such thing. So we'll use that. And remember, the k itself was j plus half. So k squared would have been just j plus half squared minus z squared alpha squared. Okay. whole. Uh, so, and then you have a n prime plus this s, which is the square root of this quantity, and this entire bracket square. This is a bad notation, so I will kind of do a better job with this. Okay, and next time I'll correct it. But uh, but this bracket should cover the entire denominator and the square of that. Okay, which is the same as s plus n square whole to the half. Okay, so that is the hydrogen atom spectrum in the when you solve the Dirac equation. Okay, so now you see that the energy spectrum depends on n prime, j, but it does not depend on orbital and spin angular momentum independently. It depends on the total angular momentum. Okay, so that is the quantity. Now, of course, like any exact solutions, this exact solution also has the same property that you get an exact answer, but you don't understand anything out of it actually. So what we'll do is that we take this equation and do an expansion of this, and then we'll understand each term in the expansion. Okay, exact answer is not as illuminating as the series expansion. Okay, so let's do that. Okay, so first thing, of course, is that there is a twofold degeneracy because the energy does not depend on L or S. So therefore, J has two different L values, L plus half or L minus half, and the spectrum is independent of which L is contributing because it depends only on J. So there are two values of L which would contribute the same J value. Okay, so the states are twofold degenerate. Okay, so what we'll do is that we'll take this expression and expand it in powers of Z alpha. Okay, so here's the expansion. Okay, so let me scroll that down to that equation. Okay, so here's the term. Okay, and we are just doing a power series expansion by saying that Z squared alpha squared upon this quantity is small compared to 1. Okay, so you get 1 minus this quantity plus various expansion pieces. Okay, so the first thing that we notice is that the leading term is, of course, the rest energy of the particle. You are doing relativistic mechanics, so you would always have this rest energy fellow going around. Okay, the next term is negative, indicating that the energy spectrum that you are looking at is a bound state spectrum. Okay, which is what we want, which is what you have in non-relativistic problem also. In non-relativistic problem, you don't have this factor 1 because you just subtract out the rest energy piece. For example, Hamiltonian itself starts with p squared upon 2m, and the rest energy piece is not there at all to start with. Okay, so there it is. So you get a correct sign to start with, bound state spectrum. It does go as z square e to the 4 because alpha is itself is alpha itself is proportional to e squared. So that's how it goes. But what you get in the denominator is a quantity which is n prime plus j plus half. Okay. Now remember, j plus half is an integer because j is a half odd integral quantity. Okay. Remember, because it is L plus S or L minus S. Okay. So what we get is a quantity which is n prime plus an integer. And what we will do is that we will identify n prime plus j plus half to be the principal quantum number that we defined in non-relativistic quantum mechanics. Okay, if you do that, then this quantity goes as z squared e to the 4 upon 2 times n to n squared, which is precisely the spectrum that you would have obtained by doing solving Schrodinger equation. Okay, that's fine. Okay, so now n prime plus j plus half is not appearing only here, it is appearing at all kinds of places. So all these places will replace n prime plus j plus half by the principal quantum number, which is what is called, which is n. Okay, fine. Now the third term, which is, yes, I can probably scroll this down. So the third term is what is called the fine structure effect. Okay, and this is a term which lifts the degeneracy uh, for different values of j, but same value of n. Okay, so this is what is called a fine structure correction. Now, this is precisely the term which was kind of responsible for Schrodinger to abandon his relativistic equation. And the problem was that he did get 3 by 8 times n, but he got minus 1 over 2j. Okay, and if you do Dirac equation, then you get precisely minus 1 or 2j plus 1, which is what Sommerfeld had written down. Okay, so you not only solve this problem of z being larger than 137 for the atomic problem to develop instability, you also uh, solve the problem of getting a 1 over odd integer sitting around here quite naturally. Okay, we haven't done anything here. Okay, now of course j itself is half integral. Okay, so therefore this quantity is could still be even or odd integer, but that is something which Sommerfeld had already factored in. So but he had a factor which is like 2j plus 1 for j integral or half integral, whereas Schrodinger had it 2j always, and that was the problem. Okay, so this is the second term. Okay, fine. Maybe I should keep this. Okay, so this is what we would get by just expanding the energy expression and comparing that with the non-relativistic quantum mechanics results and corrections which were known almost 100 well more than 100 years ago uh, and were referred to as fine structure correction. Okay, but besides this there are many other corrections that we could take into account and which you cannot take into account by just writing down the Schrodinger equation. For example, one of the corrections is what is called a finite nuclear mass correction. Okay, and this is something which you cannot in you cannot get naturally from the Dirac equation, because Dirac equation is describing motion of an electron in an external electric field or electromagnetic field. That is the kind of problem that we have solved. What is the source of that electromagnetic field was not something which we worried about when we solved this equation. Okay, so but we did something like this when we solved non-relativistic problem, where we said that like you first solve the hydrogen atom problem by just saying that electron goes experiences the Coulomb potential, and then later on you learn that like okay, the Coulomb potential is produced by the nucleus, but nucleus has finite mass. So what you need to do is to write down a reduced mass for the electron. For that, what you need to do is to choose the center of mass coordinate and then the relative mass term. That relative mass term is what is called the reduced mass of the electron. And if you replace the electron mass by the reduced mass, then all the results would that you would get would take care of the finite nuclear mass correction. Okay. Now, in the Dirac equation case, what you need to do is to treat this perturbatively. You actually introduce a nuclear mass term and kind of check the corrections order by order uh, in the mass of the nucleus. Okay.
Uh, is this because we cannot mess with the dispersion relation?
Yeah, it's because there is no way available for us to write down. If you want to write down gamma mu del mu plus mc upon h bar, you know that there is no way you can fiddle with that mass really. Okay, because it's the same mass for a free particle and the same mass for the particle experiencing electric field and so on. So what you do is you add additional interactions and treat them perturbatively. Turns out that like if you do those calculations within second order, by the time you reach second order perturbation theory, you get results which are same as the results of reduced mass. So the problem is not, I mean, a priori seems complicated, but when you actually compute it, it's not that complicated. So it has been taken into account in a more careful calculations of that kind. Okay. Okay, so the next correction is what is called the hyperfine interaction. And this is also related to the fact that we did not care about what the nucleus itself was. Okay, all we worried about was what kind of Coulomb potential that source produced. Okay, but typically nucleus is made up of protons and neutrons, and both protons and neutrons have spin. And since nucleus could be made up of multiple protons and neutrons, the nuclear spin would be a vector addition of all those spins, and that nuclear spin may have interactions with electron spin, and you need to take those kind of interactions into account. Again, simply because Dirac equation doesn't know about what was the behavior of the source, uh, these terms do not come out of Dirac equation by just converting the partial derivatives by covariant derivatives. Okay, you need to kind of uh, explicitly add these kind of pieces. Okay, fine. The third thing that we could look at are what are called higher order quantum electrodynamics effects. For example, lamp shift is one of the effect, and this effect is the one where if you look at the uh, the spectrum, then you find that the levels, if principal quantum number is 2, then S half, which that means L is equal to half, S is equal to, sorry, L is equal to 0 and S is equal to half, and L is equal to 1 and S is equal to half. These two states are degenerate. Remember, we had said this some time ago, that uh, that the states are with different J value, same J values but different L values are degenerate. So here is the situation, that S is half, of course, but L is equal to 0 and L is equal to 1. Both of them give you kind of J is equal to half state. Okay, right, by addition of angular momentum. 0 plus half is half, 1 plus half is 3 half and half. But in that, if you look at the half state, then that state and this state are indistinguishable, because they are part of this twofold degeneracy. Okay, so Dirac equation would leave them degenerate, but experimentally actually what you observe is that they are not degenerate. Okay, there is, you can actually check that there is a transition between these states, and the light emitted uh, or the photon which is emitted has 1054 megahertz frequency. Okay, now remember, as I said, that L plus half with L is equal to 1, that means P state, would also have P3 half state, which is this. Okay, and the energy difference between them is like an order of magnitude larger than this. So this split is very small, but nevertheless, this split is non-zero. Okay, and this effect is something that you cannot pick up in Dirac equation in a very simple way, because this, in to put it a little differently, in quantum field theoretic context, this is a loop effect actually. So you cannot pick it up in the Dirac equation. Okay, fine. Okay, so another thing is that, like, we wrote down the principal quantum number to be n prime plus j plus half. Okay, and j is of course half odd integral. That means it can take value half, 3 half, 5 half. That is the kind of values it can take. Okay, so uh, so n, which starts off with 1, remember principal quantum number is 1, 2, 3, and so on. Okay, for example, this is the one where the principal quantum number is 2. So j plus half will already soak up the n value to be 1. So therefore n prime starts with 0, goes all the way up to n minus 1. Okay, because this fellow can, the lowest value j plus half can take is 1. Okay, so therefore it can go up to n minus 1. Okay, fine. So so if you take the largest value of j plus half, or largest value of j, that would of course soak up the principal quantum number completely. Corresponding to that, n prime would just be 0. Okay, now for that case, you have only one fold degeneracy, remember, because you get k, which is only j plus half. Okay, the other value for j that we could have obtained, okay, it would not be accessible. Okay, so this is something we had talked about earlier also, that in uh, if you look at the highest value of j, then the highest value of j comes as L plus S only, when you do a vector addition, L plus half, and there is no contribution coming from L minus half piece. Okay, there is no L minus half piece coming, because to get higher value of L, uh, remember in non-relativistic quantum mechanics, L is bounded by n value. L can take value going from 0 to n minus 1. N is equal to 1, which is the ground state, is always only s orbital, which is L is equal to 0. N is equal to 2 has only s orbital and p orbital, and so on. Okay, so p is of course has L value 1 and so on. Okay, so whenever you take highest value of j, it is not twofold degenerate, simply because L minus half is not contributing. Okay. Now, there's another thing that we had already observed, was that k takes values which are plus or minus j plus half, and if you fix the j value, then opposite k values would have opposite parity. It is related to the same fact that if you write it in terms of L, then you can show that uh, if plus sign corresponds to even parity state, the minus sign would correspond to odd parity state. Just a few lines of, I mean, back of the envelope computation really. Okay. So any questions at this point? Okay. If not, then we can kind of continue. Uh, the angular part of the wave function, yeah, please.
One thing,
Yeah.
we like even in our periodic table and all, we usually just classify using N, L,
And S.
M and S, yeah.
Yeah.
So, but that N and L are obtained through Schrodinger's solving, right?
Yes,
Like,
that is right.
shouldn't we like reorganize the table then?
Well, it will give you the same set of quantum numbers. Yeah. Nice try.
But we have extra degeneracy here, at least apparent degeneracy, which
Yeah.
apparently will go away when
Yeah,
we
it will go
solve.
away. Yeah, it will go away. Like when we start doing atomic physics, you will see that, like, what we'll do now is, we are not going to solve Dirac equation for atomic physics. We'll solve Schrodinger equation, but all the terms, all the relativistic corrections, or all the corrections coming out of the Dirac equation will be reincorporated in the Schrodinger problem. But we'll mostly solve the Schrodinger equation. And part of the reason is that the energies involved are not so high for any of these particles being relativistic anyway. Okay, so therefore solve the non-relativistic problem, take relativistic corrections into account. Okay, and if you find in a specific case the relativistic correction is too small, okay, then you ignore those. Okay, that is how we are going to do atomic physics, in fact. I would presume that is precisely the reason why the periodic tables are mostly written in the non-relativistic set of variables. If you of course work with these set of
But
variables and work them out correctly, you will still get the same quantum numbers really. Quantum numbers
yeah,
cannot
but
change.
we have extra degeneracy which we don't really see there, I guess. I'm not sure whether we like, because we start off by saying that once we fill the lower energies first,
Yeah,
starting from the lowest value of N, then
yeah,
L, because the energy is in terms of that.
that's right.
And then and the degeneracy is only in M and S, the
Yes, yeah,
angular quantum number and that
yeah.
uh, spin. Yeah. But apart from that, we don't have a degeneracy. Is the
That's
degeneracy that we are seeing here like
that is
same
precisely
as
the
that?
same. Yeah, it's exactly same, because this J is written as L plus S. No, I'm writing S to be half all the time, but it is actually L plus S. So the degeneracy that you see in terms of L and S in the Schrodinger equation is the same degeneracy that you see here. It is just that, like, we are working in the basis which in the angular momentum language corresponds to what is called LSJM basis, or LSJMJ basis. Okay, which turns out to be a suitable basis to work with here. The natural basis that you would work in non-relativistic mechanics, where angular momentum is appearing naturally and the spin has been put in by hand, is LSMLMS basis. Okay. In the Dirac equation, spin is not put in by hand. It also appears naturally in the equation. So therefore, L plus S is a natural quantity. In non-relativistic problem, L plus S is not a natural quantity because L is part of the equation. It has appeared naturally from the Laplacian. S is something that you have put in by hand.
But and above we have written when we take some QED corrections into account, even
Yeah,
that degeneracy breaks.
that is right. Yeah,
The
at
spin
this level.
thing.
Yeah, at this level, yes. Yes, lamp shift effect is but quantum correction really. I mean, okay, in quantum field theory, when you say quantum correction, that means it's a loop effect. Okay, uh, so that is a higher order thing that neither non-relativistic nor relativistic mechanics actually picks it up. You need full
Okay.
quantum field theory for that.
All right.
Okay, okay, good. So let's get to the angular part of the problem, okay, which already we have kind of claimed that we have solved it. Okay, uh, the wave functions are basically eigenfunctions of this operator, h bar times k, and k was of course beta times, or rather h bar k was beta times L dot sigma plus h bar. Okay, and uh, this operator has opposite eigenvalues for the upper and lower components. Okay, if you write it down in terms of sigma matrices, you can see that they are kind of appearing this way. Okay, fine. So, so what it tells us is that, like, because of the spherical symmetry, we knew that the angular part of the wave functions would be spherical harmonics, but there is of course naturally a spin occurring in Dirac equation. So therefore, the total wave function should be YLM theta phi, which are the spherical harmonics corresponding to orbital angular momentum of the particle tensored with the up down state. Okay, which is the Pauly spinor. Okay, so I just wrote it this way just to indicate that it's a two component spinor, not that both the terms are necessarily non-zero, but that's how it will appear. Okay, fine. So therefore, you can write these in terms of the j variable, which is what I was trying to tell you is the natural variable that you would get in Dirac equation. These are the variables that you would get in Schrodinger equation because L and S are are independent quantities in some sense. Okay, one occurring naturally in the equation, other is put in by hand. Here, both of them occur naturally. So you work in the j basis. You write down the wave function, which I call small y L, uh, and you write the upper component as capital Y L m minus half, and the lower component capital Y L m plus half. Okay, so that is the form of this wave function. Okay, with a normalization of this kind where you say that j, mj, and L values have to be same for this wave function to be ortho or to be normalized to 1. Okay, fine. Okay, so what we need to do is to combine these two component spinors. Remember the total spinor of course has to be 4 component. Okay, so we are going to combine these two component spinors to write down a 4 component spinor. Okay, so uh, and to do that, like, since j is a correct kind of quantum number in the Dirac representation, we will choose the uh, upper and lower component spinors to have the same j value. Okay, fine. But if you choose them to have same j value, they would differ by 1 when you look at their orbital angular momentum value. Okay, so therefore the parity of the upper component is different from the parity of the lower component. But that is just as well because we have already studied that the parity transformation of the spinor is done by the matrix gamma 0, or which is the same as beta, and in our basis beta was diagonal matrix with identity and minus identity. So therefore, under parity transformation, spinor would be multiplied by beta, which tells you that the upper component does not change sign and the lower component changes sign. Okay, this is consistent with what we found here, that if you work with the good quantum number in the Dirac equation, then upper and lower component would have L values differing by 1. Okay, fine. So, so this is just some remarks that, if you want to get a change in the L value, all you do is you write down the upper component to be something, say 10, something like that, and you write down the lower component to be sigma dot r times 10, and object like this would switch the L value by 1. Okay, not very. Uh, I mean, I am not going to elaborate on this one, but if you really want to write down these quantities, these four component spin-offs explicitly, this may be one kind of way of writing down relative factors between upper component versus lower components and so on. Okay. So this is equivalent statement to what I said, that if you multiply by sigma dot r to j minus plus half, you get a answer which is minus j plus or minus half, and that's why it swaps the value of the j from j minus half to j plus half. Okay, and that switch would require L to shift by 1, uh, since S is fixed to be half all the time. Okay, so, and the point is that sigma dot r hat not only takes j minus half to j plus half, it also swaps j plus half to j minus half. Okay, so therefore it can take you both ways. So you don't have to work only with the particle solution, that means upper component large and lower component small. You could work with antiparticle solution also, which is upper component small, upper two components small, and lower two components large. In both cases this operator would do the job. Okay, fine. So finally, the simultaneous eigenfunctions of J, K, parity operator, and the Hamiltonian are written like this. Okay, if K is J plus half, then it takes this kind of form. You have Y J M J minus half and Y J M J plus half as upper and lower components. These are radial wave functions. And if J is negative, then J plus half is upstairs and J minus half is downstairs. Okay. Now remember that these Y's are already two component fellows. Okay. The small Y's were already two component guys. So when you write down two of them, this wave function is already a four component spinor. This 1 over r factor, as we discussed right in the beginning, was to simplify the radial Laplacian. Gr and Fr are the solutions that we would obtain by solving the radial uh, part of the equation. Okay. So this is, I am not giving you exact form of G of r and F of r, uh, but it should be obtainable. Okay, one can write down. You need to fix the quantum number n prime to be some value. These functions corresponding to that value, these functions are known. Okay, and they are same as Legar polynomials actually. Nothing new there. Okay. So any questions here?
In the below thing, could you go to the Y form, the matrix form?
Yes. Just hold on. Huh? Yeah.
How did we? Achha, this is just solving the angular part.
These are in the angular part. Yeah. And in the lower part I have written YL, but in the upper part I'm writing L in terms of J, because J is a good quantum number. That's why it is J plus half and J minus half kind of factor sitting around. But that is actually the L orbital angular momentum value. Okay.
Also, usually, if I remember correctly, we got Legendre polynomial in this case also, right? When we solved the
Yes.
Schrodinger case.
Yes. So that is what these are. YLMs are just Legendre polynomial times e to the I n phi or something. No. Remember I said that the wave functions are. Where did it go? Sorry, it must be right there. Yeah, here, right?
Yeah.
YLM theta phi are same as PL cos theta, which are the Legendre polynomials, times e to the IM phi, right?
Yeah.
So it's the same stuff. Is that fine?
I'm just thinking whether the radial part, what the radial part there was.
Oh, the
The
radial
radius
part in
between
the non-relativistic problem?
yeah,
They were that differential equation had a Legare polynomial as a solution.
and even this has that.
Exactly, same solution.
That is confluent hypergeometric solution.
Yeah. The equation is confluent hypergeometric equation. Solution is Legare polynomial. Confluent hypergeometric, depending upon what kind of singularities you have, has different solutions. But in this particular case, it's Legare. You could also
Exactly.
have
We need to incorporate some constants in that function.
which constants?
That I mean, in the differential equation, we have some function. In confluent geometric differential equation.
Yeah.
So that function depends on n dash and some other constants. We need to incorporate what is n dash and what is other values. What are other values?
No, that is true. But confluent hypergeometric equation has various kinds of solution depending upon what kind of functions you choose. For example, Bessel function is also a solution to confluent hypergeometric equation,
Yes,
right?
yes.
So in this particular case, you get Legare polynomial and not Bessel, for example. Okay. So
Okay.
yeah, so that's why confluent hypergeometric is a more general statement, but in this particular case, we know exactly what is the differential equation. It is of course confluent hypergeometric in the sense that, okay, confluent hypergeometric function is just or equation is just a name. To put it in just simple language, if you have a differential equation which has a regular singular point at r equals or x equals 0 and a regular singular point at x equals infinity, that class of second order ordinary differential equation are called confluent hypergeometric equation. Okay. If we go back a few slides, you will realize that we had actually r equals 0 as a regular singular point and r equals infinity as a regular singular point. So in that sense, our equation falls into what is called confluent hypergeometric equation form. Okay. But confluent hypergeometric equation can be of various kind, because if you have a irregular singularity, there is no limit on how bad that singularity could be, and it would still be confluent hypergeometric. Okay. So depending upon how bad your irregular singularity is, you get different solutions. Our our equation had terms falling off as 1 over r, but you may have terms which is falling off to infinity as 1 over r squared, r cube, r to the 1 over r to the 10, anything. All of them are confluent hypergeometric, but solutions may differ. Okay. In this particular case, the problem is solvable. If you have 1 over r to the 10, you may not even be able to solve it.
Yeah, sir. Yeah.
Okay.
Okay, sir.
So any other question? Yes.
You said that even here we can give some sort of a probabilistic interpretation,
Yes.
like we used to give in Schrodinger case.
Yes, eminently.
And also, I asked this earlier also, but I'm not so clear about it. But
Okay.
even though we are solving for a single electron system,
Yeah,
we are getting a 4-component spinner.
that is right.
Then why do we shouldn't make that statement, right? That the upper 2 components correspond to the electron and the particle, and the lower 2 components correspond to the antiparticle.
Yeah, we shouldn't be making that statement. Actually, electron is entire 4-component spinor.
Yeah, and even the the
Yes,
positron is a
positron is also
4-component
entire
spinner.
4-component spinor. Okay, only when you kind of take non-relativistic limit, you find that the upper component is larger for a particle and lower component is larger for the antiparticle. But when you actually talk about solution, entire spinor is a solution. It's not like upper component of it is something.
Yeah. Okay.
Yeah. Any other question? Okay, if not, then we'll change the topic. And the next topic is basically something which uh, is really something which is going to be useful for what we'll do in atomic physics. And that is that we are not going to solve Dirac equation every time we do atomic physics, but we would solve Schrodinger equation, and we would use the terms which come from Dirac equation, add them to the Schrodinger equation as relativistic corrections or various other kinds of corrections like, spin orbit correct terms and so on, and solve the Schrodinger equation problem by adding these pieces in a piecemeal fashion. Okay. So to determine what are the kind of terms that you would get, we will do what is called a Foldy-Worthausen transformation. This is a transformation which tells you how to bring Dirac equation in a diagonal form, and if you can diagonalize the Dirac equation, then you should be able to obtain the spectrum of Dirac problem exactly, because finally all you are interested in is in diagonalizing the problem. Okay. So what we'll do is we'll do this Foldy-Worthausen transformation. First thing that we will do is take free Dirac equation, and in that case, of course, you can show it exactly, uh, and uh, and then we'll kind of go over to the problem where Dirac equation is interacting with the Coulomb potential, and in that case, of course, you cannot do it exactly, because if you could, then of course, we would have obtained all kinds of right kind of terms that you could have added to Schrodinger equation. So that's not what happens. So we will kind of systematically write down terms order by order in V by C. Okay, and we will see how it proceeds. Okay, fine. So so this is a statement that one gets to hear quite often, that if you try to take a non-relativistic limit and if you look at the particle degree of freedom in the Dirac equation, then the upper component is large and the lower component is small, and that is because the lower component is v by c times the upper component, and if the velocity of the particle is small, then v by c is small, and therefore you call the lower component to be a small component and upper component to be large. And in that case, you get effectively, to leading order, you get effectively two component spinor, which is what is the quantity that we used in the Schrodinger equation. Okay. uh, so having said all that, we still want to ask, how do we actually reduce this problem such that we could utilize these terms to study, say, Schrodinger equation. Okay. Okay. So if you are studying the free particle, then what you want to do is to actually diagonalize this problem so that you can pick up even the subleading corrections and bring the Dirac equation into a block diagonal form and determine the spectrum. Okay, so it's a free particle Hamiltonian once again. Okay, now maybe I can move this out. We don't need it now. Okay, so what we want to do is to diagonalize this quantity. Okay, in this we already know that beta as a matrix is diagonal, but alpha is not a diagonal matrix. It is off diagonal sigma uh, sigma matrices. Okay, it is sigma sigma off diagonal, and we want to kind of diagonalize that piece. Okay, good. So so of course, we can reduce this equation to a diagonal matrix by just doing a Lorentz boost. Okay, this Hamiltonian corresponds to a statement that when you act on a particular wave function, if p gives you a non-zero answer, then that particle is moving with certain momentum p, and therefore it is not at rest. And there is a contribution from the momentum, and then there is a rest energy contribution coming from mc squared. Okay, if mass is non-zero, then you can always go to a frame which is a rest frame of the particle. In that case, alpha dot p acting on the corresponding wave function will give you 0, and you have a diagonalized Hamiltonian. Okay, but that is kind of a cheating in the sense that, like, you basically just get rid of this piece by working in a frame in which the momentum operator has 0 eigenvalue. Okay, so what we want to do is not do that, but keep alpha dot p, but find out a unitary transformation which changes psi to e to the I times psi, sorry, e to the I times s multiplied by psi, and h, which is an operator, undergo this conjugation transformation, e to the is, h e to the minus is. Okay. What we want to do is to find appropriate s such that this new quantity that you write down, let's call it h prime, is diagonal. Okay. So that is the game. Okay. So I'll just tell you what is the transformation. One can try to figure out what it is by systematically checking what kind of terms you would require by expanding this object and looking at pieces in this expansion. Okay. Now, if you take e to the is, h e to the minus is and expand both exponentials, that is same as the Baker-Campbell-Hausdorff formula that we talked about in some other context, in some other lecture. Okay, but it's the same formula. Okay, we will write it down once again, but uh, but what you will get is something like this. You will get a term which is h plus commutator of s with h, then next term will be commutator of s with commutator of s with h, and so on. And then what you do is that you expand, look at a few terms and ask, and how do I diagonalize the piece? You know already that first term would be h, which already contains the off diagonal piece, which is alpha dot p. You want to look at a term which is a commutator of s with h, and you ask whether that commutator contains a piece, off diagonal piece, which is with the opposite sign, such that it cancels the off diagonal piece in the Hamiltonian. Okay, off diagonal piece in the Hamiltonian is alpha dot p. You check what kind of s that you can write down such that the commutator of s with h will produce a off diagonal term, namely this, but with the opposite sign. Okay, the that is the rule, and answer is of course beta times alpha dot p. Okay, one can kind of systematically work it out, as I said. Okay, the angle theta uh, is kind of related to momentum and mass in this particular form. This is nothing new. We had seen this relation earlier also when we kind of uh, we said that we have a rectangle, right angle triangle, and with one direction proportional to momentum, other related to proportional to the rest mass, and you get the diagonal of that right angle triangle uh, to be the eigenvalues. We had done this when we studied the Klein-Gordon equation. Okay, analysis is same really. Okay, fine. So you use this and compute this quantity. Okay, you get a Hamiltonian h prime, which is written as beta times square root of p squared c squared plus m squared c to the fourth. Now you may think that this is cheating. After we of course knew that this is going to be the answer. Beta tells depending upon which component is going to contribute will tell you plus or minus value, and which is precisely what Dirac did not want. And here is the answer. Okay, you do get plus positive and negative eigenvalues for the energies and the same relativistic dispersion relation. Okay, now that you could do this for a free particle is in a way good, but in some other sense you shouldn't be surprised, because you would have expected this to happen for a free particle. Okay, simply because you chose to write the equation in matrix form cannot deny you the fact that the energy spectrum is going to look like this. Okay, and there must be some similarity transformation which diagonalizes the problem to give you this spectrum. Okay, but nevertheless, what it at least tells you is what you need to do is to do a similarity transformation, and the role of the similarity transformation is to rein in the off diagonal component sitting inside the Hamiltonian and try to make it as diagonal as possible. Okay, for a free particle case you actually just diagonalize it. Okay, but if you have an interacting system, that means suppose you don't have just p, but you have p minus e by c times a, where a is a vector potential, and in addition maybe you have e times phi, which is like the Coulomb potential. Then in that case you need to ask a question, because nobody is telling you what a vector potential a is. Okay, and nobody is telling you what phi is. Okay, of course you could choose phi to be a Coulomb potential due to nucleus or some such thing, but if you don't make any such assumptions, then for arbitrary vector potential and for arbitrary kind of time component of the gauge potential, you want to ask a question: how do I diagonalize? Right. So that is the next thing that we would like to do. Okay. So as I said, that we could do similar things for the hydrogen atom problem. Only thing is that when you do this, you cannot do an exact diagonalization. Okay. So what we'll do is that we'll extract terms order by order in the fine structure constant alpha. Okay. And interpret the higher order terms uh, as perturbative corrections to the non-relativistic problem. Okay. That is what we want to do. Okay. Uh, Actually, I shouldn't have said alpha. I mean, it is a power expansion in alpha, but it's an expansion really in terms of V by C, or it is expansion in terms of 1 over m, 1 over m, where m is the mass of the particle. When you are doing non-relativistic problem, then the mass of the particle is much larger compared to the energy spectrum of the quantum mechanics problem, because um, the energies involved in, say, a hydrogen atom is of the order of 13.6 electron volts, as against electron mass, which is like 511 kilo electron volts. Okay, so it's like almost 5 orders of magnitude larger rest mass. So what you could do is, instead of doing alpha fine structure power expansion, you could have done 1 over m expansion. Pull out mc squared and write down all these quantities as 1 over m. You could do that also. Okay. Uh, if you say that the mass is very large, then of course the momentum is small, and therefore that 1 over m expansion is same as v by c expansion, because the velocities are small. Okay, they are all equivalent statements. Okay, fine. So what we'll do is ask the same question, but now for a Hamiltonian, which is a little more intricate than the free particle. Okay, we will do the same similarity transformation. Of course, not the same S. Okay, we'll have to determine what this S similarity transformation matrix is. Okay, and that we will kind of do in steps. Okay, so as and when kind of so as I said, that like you cannot completely diagonalize the electromagnetic interactions of Dirac particle problem. So we will first diagonalize some piece of it, and then we look at the remaining piece, and then we try to do a transformation which diagonalizes the remaining piece. Okay, that is the kind of stuff that we'll do. Okay, so although formally I have written down e to the I s times psi, we will write s in a kind of multiple pieces. As we progress, we'll see what happens. Okay, fine. So if psi prime is this, then psi is of course e to the minus is times psi prime, and the equation is I del t of psi is equal to h psi. That is the equation, which is written as I del t of e to the minus is times psi prime. Okay, this quantity can be expanded, either the derivative acts on psi prime or the derivative acts on e to the minus is. Okay, so here are the two terms. Okay, what we'll do is we'll collect I del psi prime by del t on our side, on the left side, and rewrite the entire expression in terms of h psi prime. Okay, so of course h is actually acting on psi, but you can introduce e to the minus is and e to the plus is inside that. Use e to the plus is times psi to be psi prime and write down this expression as this term. The second term is just taking this piece on the left. The first term is the piece where you have uh, multiplied e to the minus is and e to the plus is between h and psi. E to the plus is times psi is written as psi prime. Okay, that is the expression. Okay, so you can collect these terms, and you can see that h prime is actually a similarity transform of h minus I del t. Okay, that is the quantity that we are going to look at. Okay, so our exercise boils down to finding out this matrix S such that H prime is as diagonal as possible. Okay, given the fact that H that we are going to look at is a problem of Dirac particle interacting with electromagnetic field. Okay, fine. So here's the same statement that we want to choose S in such a way that the off diagonal part of H prime is minimized. Okay. So of course, what one means by minimized is it depends on to what level of accuracy you want to do a computation. Okay. So you want to do a computation to a particular level of accuracy. If the off diagonal part of H prime is smaller than that, then you can happily ignore it. But if it is not, then you will have to do a transformation to diagonalize that piece until the off diagonal part is smaller than what you are interested in. That is the rule of the game. Okay, is this fine? Okay, so here is the Baker-Campbell house the formula again. Okay, written little differently, but this is the one which is relevant because our H prime is exponential is H exponential minus is, and then there is a term which is exponential is derivative acting on exponential minus is also. Okay, for which you need a different kind of formula which I have not written down, but I guess I should probably write it down. That would be useful. Okay, fine. So this expression is an infinite series with nested commutators. Uh, all you need to do is to expand e to the I lambda s and e to the minus I lambda s and take product and collect terms which involve same power of lambda. Okay, so that is the easy way of doing it. Like for example, the leading term is a term which is lambda to the 0, and that would just give you the operator O. A term which is proportional to lambda is a term which would contain one s, and that s could be either on the left of O or on the right of O. And if it's on the left, it will have one sign. If it's on the right, it will have opposite sign because of this minus sign in the exponent. Okay, but that would correspond to a commutator, and that will give you SO commutator piece. If you keep doing that, you can check that O appears always linearly because that's the only way, because it is linear in this equation. But S doesn't appear linearly simply because it's when you do exponential expansion, you get quadratic, cubic, higher powers of S depending upon to what extent you expand the exponential. And that is why this commutator contains multiple powers of S, but only one power of O. Okay. Other terms are kind of trivial to guess. I lambda to the nth power divided by n factorial is a natural exponential expansion that you would have guessed. Okay. Fine. So what we'll do is we'll use this formula to determine h prime to any desired accuracy. Okay. Whatever to what power of v by c that you are interested in. Okay. And what we'll do is we'll work it out up to order v by c to the 4. Okay. So that is what we will do. Okay. But what I'll do right now is that I'll probably stop here and we'll pick it up from this point in the next class. Yes. Okay.
Uh,
Yes.
you said something about uploading handwritten notes or something.
Yes. 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 I will do them today because you see, yeah. Let me stop recording. I don't want to record this discussion.